Thank you for coming. It's very nice to be here, talk to you about a particular enthusiasm of mine, which is green software. My name is Owen Woods. The reason I'm talking to you this evening, stopped, is that, in my opinion, in many people's opinion, climate change is the most pressing problem facing mankind at the moment. There are obviously geopolitical tensions at the moment, which arguably in the short term are even more important. But one thing we can be sure of is, if the climate emergency gets worse, geopolitical factors all over the world, water, heat, access to resources, are only going to get worse. So I would argue climate change is actually the most important, even in the short term. The thing is, at least I, perhaps in my ignorance, until a few years ago, really thought that climate change was all about airlines. You shouldn't take long-haul flights you don't need. You should fly in economy class because you get more people per unit of emissions. It's all about people who make steel, people who make concrete, and the software industry didn't have too much to do with it. And then, unfortunately, I was much happier not knowing. Then I got a bit closer to the whole question about sustainability, ICT. They generally bundle us together with telecoms, the ICT industry, specifically software. I discovered that actually ICT emits between 2 and 4% of global emissions. There's a lot of debate. I'll talk a little bit about emission measurement later. Everything's an estimate. Well, that doesn't mean it's wrong. It tends to mean that scientists will give us a range of values rather than a precise value, but that doesn't mean that they're not valid ranges. So most estimates put us in the 2 to 4%. And it's getting worse. That doesn't sound too bad until you realize that aviation, who are like the bad character in the room, they're 3%. Of course, there are other industries. Deep water logistics is not very good. Concrete is particularly bad. Steelmaking is also bad. But frankly, as a supposedly clean industry, if we're producing 4% of global emissions and it's getting worse, we have a problem. Arguably, the bigger problem actually is the growth rather than where we are today. This, in fact, predates AI significantly. Everyone knows that I think AI potentially has bad environmental impact, but actually the growth was happening well before AI. So you can imagine AI is actually compounding a problem we already had because the world is becoming more digital. We are building more data centers. We are using more power, and AI has simply increased the rate. It's not actually introduced new growth. A few slightly frightening estimates are data centers might use 5% of electricity by 2030. And you want to guess what the emissions of a country like, sorry, not the emissions, the electricity use of someone like Germany is? Globally, it's about 4%. Data centers by 2030, and actually these are quite conservative estimates. I recently read a couple of white papers from IEA and other organizations. These are 18 months old. They've actually even more pessimistic views now. Because of things like the deals being done in the Middle East recently. To give one example, I'm not picking on Microsoft, they're actually almost good guys in this. Microsoft admitted freely that their greenhouse gas emissions, I think last year was 2023, went up by 30%. And they can tie that pretty well back to their investment. The fact that they have a huge amount of AI training going on, but even worse, they have a huge amount of AI inference going on. And that's every time you ask a model running on Azure to do something clever, something critical to your life, like generate an emoji. That's all using compute power. And compute power eventually becomes emission. So that's why, when I discovered all this some years ago, I suddenly realized that perhaps we have our role to play in solving it. And talking about growth, all the database studies, this is from what scientists call a macro study. This is where somebody studies all the other studies. You don't really need to understand any of the detail other than all the graphs are going in the wrong direction, as in emissions increasing and quite fast. Really, the debate is how fast, not are they increasing. Other industries, you may well be aware, because of all their PR, some of it being greenwashing, but some of it actually being very solid, most of their graphs are flattening out and going down. We're one of the few industries where the graph continues to estimate to go up for the indefinite future. So we could, in fact, get sort of worse and worse relative. The question is, why am I standing in front of you and talking about this? Today I'm an independent consultant. I've recently left a company called Endava, who are well known to Zulka, for example. We're in a similar business. I was chief engineer there for 10 years. And before that, I built various kinds of software for quite a long time. The reason I discovered all this and the reason I became very interested in it was I did a PhD in industry part-time. Started in software architecture for various reasons I won't bore you with, pivoted to energy efficiency. Because back in 2015, 2016, that's actually what we call green computing. We call it energy efficient computing. Today it would be a PhD in green software because that's far trendier, but it's exactly the same stuff. The energy efficiency is fundamentally one of the building blocks of making software green. So that's why I got into this. We'll briefly talk about what the fundamentals of green software are. We'll talk a bit about, a fairly shallow level, about some principles and tactics we could use to try and start thinking about what emissions we're producing and also measure and reduce them. We do have to talk about AI. The early versions of this talk didn't talk about AI, and then ChatGPT happened, and the whole world started asking ChatGPT to make up poems for them. And that's, of course, as we've just said, increasing emissions a lot. So I'll talk a bit about how an AI-oriented company might think about their emissions. Now, I've got a couple of case studies I'll go through fairly quickly. I won't test your patience too much. But then I think the most important section is at the end. I've got some advice, really based on the journey that we were on at Endava and with some clients and personally, as to where you might start and how you might direct your effort if you want to think about emissions with the software systems you're involved in. So green software fundamentals. Firstly, on terminology. I should have asked. In the room, has anyone heard of the Green Software Foundation? Is anyone a member of the Green Software Foundation, for example? Is anyone active in Green Web? Just kind of wondering kind of people's backgrounds. Yeah, so some of you are, great. Everybody talks about carbon, which is a very, very unfortunate piece of terminology, because carbon, chemically, carbon is nothing to do with greenhouse gas emissions. It's a cute kind of reduction of carbon dioxide, which is actually the gas, one of the gases that we are concerned about in environmental change. It's not even the most dangerous gas. This is the irony. There are many more dangerous gases, just that we tend to produce a lot of CO2. That's when people, even the Green Software Foundation, talk about carbon and carbon-aware computing. That's tremendously unhelpful. They really should be talking about greenhouse gas aware computing. But anyway, I talk about greenhouse gases. If you hear people talking about carbon in this context, it's exactly the same thing. There's two sorts of emissions we need to be concerned about for almost anything, actually, but in our world, we can be quite specific. For software systems, there's two sorts of emissions. There are embodied emissions, and those are the emissions that we indirectly generate by wanting to run a software system. So they are emissions related to the entire supply chain, from digging lime out of the ground to make concrete, to pulling rare earths out of the ground to create silicon chip manufacture, PCB manufacture. All of those things are all the supply chain. We indirectly, I never really thought about this, but we indirectly create quite a lot of construction. Data centers are large, and we keep building them, at an unimaginable pace. Data centers are almost always poured concrete structures. Concrete is the most environmentally damaging way to build a building because the production of concrete and cement produces an awful lot of, it is in fact in that case carbon dioxide. So we tend to pour a lot of concrete, and that's construction. There's also steel. Steel isn't particularly good for the environment. Data centers are basically concrete and steel, if you look at how nearly all of them are built. And then there's the hardware manufacture process. There's a lot of emissions involved in, there's also a lot of nasty waste products, but we'll gloss over those. There's a lot of emissions in manufacturing a piece of hardware, be it a teeny tiny sensor, be it a consumer device like an iPhone, be it a huge rack server for use by, computational computing. That's embodied emissions. It's about creating the physical environment we run the software in. The other sort of emissions are operational emissions. The operational emissions are any emissions generated by running our software. And to a first approximation, to almost entirely precise approximation, that's energy. It's how we generate the electricity that powers our data centers. There are other tiny amounts people drive to and from data centers to operate them. Data centers themselves and some other emissions, minor emissions caused by operation, but really it's all about the electricity. Of course, electricity is generated in very different ways. If you are, not to pick on countries, but if you're in Poland, you will almost certainly be using electricity generated using coal, same in India. If you're in the Nordic countries, you'll be using a lot of energy generated using hydro. If you're in France, you will be using a lot of energy generated using nuclear fission. Now, those different production methods have got very different quantities of emissions associated with them. Clearly, if you're running a lot of data centers in Poland, you have to accept that electricity will be producing a lot more emissions than if you're running data centers in Oregon in the USA or in Scandinavia, where it's probably hydropower you're buying. And most grids are a great mix across different sources, and the average of it, the weighted average over time, is known as the grid carbon intensity. That's real, and that varies over time. For the British grid, I'll show you how you can get all this. For the British grid, that's available in real time, second by second, our grid carbon intensity. And that tells you how, for a certain amount of power, the quantity of emissions that would be produced if you consumed it now. And of course, there are predictive models and there are analytical models going back into the past. Embodied emissions are quite interesting because we sometimes, certainly as a server-side developer, I've tended to forget about consumer devices. I always think they're not really my problem. People use them to display the browsers that display the software that, by magic, we produce on the servers. What's really interesting, though, is if you're thinking about this embodied versus operational emissions, they vary dramatically across different devices. These are real numbers from real manufacturer data volunteered by the manufacturers. So this isn't an environmental studies department at Southampton University making it up, or estimating it, as they would call it. Neither is it a journalist having a guess. These are real validated numbers, externally audited from Apple and Dell. Yes?
They've all been normalised, haven't they, to 100%? So
yes, sorry, I'm not giving the absolute numbers. This is about the life cycle, actually, rather than the absolute numbers. I do have the absolute numbers of a spreadsheet, if you're interested. The iPhone 14, 80-something%, I think it's 83% of its emissions are embodied. Operating it, because, of course, mobile devices tend to be extremely energy efficient, operating it doesn't actually create very many emissions at all over its entire life. This is obviously an estimated lifetime. I'm not sure what the lifetime is. At the other end, a Dell server burns a tremendous amount of electricity, and they tend to run non-stop without being shut down for years at a time, with very, very brief reboots. So nearly all of its emissions, in percentage terms, it's like 18% or something, are operational. That's quite important to remember when we're thinking about the overall emissions we're responsible for, because we tend to worry about this, and there's an awful lot of people running around giving conference talks about start to use green electricity, and that's very sound advice. But if you accidentally, because you don't think about it, end up forcing people to upgrade their iPhones very regularly, which in a corporate environment, perfectly reasonable, you've all got the whole fleet's going to have to be upgraded because we're going to use the security software. Actually, there'll be huge implication for the embodied emissions for that firm that year. It's important to bear that in mind. When we're talking about operational emissions, as I say, we're talking about the greenhouse gas intensity of the grid. The picture on the right is from a company called electricitymaps.com. And if you can't bear to wait, by all means, bring it up on your phone now. There's a live map on the front page. It gives a global view, though it's quite Eurocentric, both historical data and live data about the estimate of the, I think they call it the carbon intensity, but the greenhouse gas intensity of a particular grid. Obviously, the emissions we create are the product of the amount of energy we need, the amount of energy we desire to use, multiplied by the intensity of the grid. So if we use a relatively small amount of electricity, someone that burns a lot of coal, that's you, Poland, we might produce the same amount of emissions as a vast amount of electricity in France, for example. I do realise nuclear power being seen as a green energy source is extremely contentious. Can we just gloss over that and move on? There are some academics I am friendly with who at this point would be screaming and shouting and leaping around in their chairs, but it doesn't produce emissions in the sense of greenhouse gas emissions. I do accept there are other side effects. But this is the operational emissions calculation. If we can, for a unit amount of demand, clearly if we can drive down the intensity of the greenhouse gas intensity, we will use less emissions. So the question is, what can we actually do about it? When you first look at this problem, I can assure you, even in a research environment, it looks pretty intractable. But actually, a lot of people have been thinking about it now. We inherited a lot of work done in the 2010s, I suppose, in the mobile device community, because a lot of research did a lot of work on how to preserve power, because they weren't worried about emissions, they were very, very worried about batteries. A lot of the principles that they came up with were very useful to then scale up. And since then, in by 2018, a lot of people, both cloud providers through to enthusiastic individuals, have been thinking about what could we do to make our overall system's lifetime emissions more reasonable. We could have principles to guide us in how to behave. We could have specific architectural tactics. Design it like this, it will reduce the emissions. There might be some design patterns we could use. And who knows, there could even be some software tools. In fact, all those things exist. And for the purposes of this talk, we'll have a look at some principles and some tactics that you can sort of take back to work tomorrow and start thinking about applying. Green Software Foundation are the best funded, best known organization in this space. They're well funded because they're part of the Linux Foundation and they charge very, very high fees for corporates to be members, so corporates can talk about being part of green software. As a funding model, it works extremely well. Whether it always produces the best results, I'll leave you to go and read their website and consider. But what's important about the GSF is they're very visible, they have extremely good marketing and PR, and they've done more than anyone else to raise the profile of the importance of thinking about sustainability in software. They've come up with 6 principles, all of which are perfectly valid, some of which are a little bit vague, but they're all perfectly valid principles. And it's not a bad place to start. One big advantage is, if you say they're the GSF principles, your CIO tends to go, who are the GSF? And when you say all of these companies remember, they'll tend to go, oh, okay, well, those must be okay then. As opposed to, here are some principles I thought up yesterday. I can assure you they're very good. They come with a sort of implied stamp of approval. That ThoughtWorks, who Andrew Harmon-Law works for, ThoughtWorks were one of the founder members, and our big competitor EPAM, are also, sorry, not EPAM, Cobalt are founder members as well, along with Accenture. So the 6 principles they've come up with are: emit the least amount of carbon, greenhouse gas carbon possible, which sort of sounds obvious. What they're really saying is, if you don't think about that, you're very unlikely to minimize it. So the first step is start thinking about how you reduce your greenhouse gas emissions. And that leads you to the second point, which is operationally, it's nearly all about the electricity. So reduce the amount of energy you're using. Now there's an interesting trade-off there, which the GSF don't go into in principles. It's buried away in a patterns catalog. Do new computers or old computers use more power for a unit amount of work? Yeah, old ones, exactly. If we throw away all of our old computers and use new ones for the same workload, we should use less power and therefore create less emissions. What's the problem with that? Well, you need emissions. Yeah, so there's actually quite a difficult trade-off there, and you need a lot of data to make a good decision. My PhD supervisor, Ravi Basrouche, who's a professor at UEL, has actually done some quite pioneering work to create a model for that, which the EU have been trying to apply. But it is a difficult trade-off. But fundamentally, we need to think about how do we reduce the energy. And also we accept that all grids, even hydro-based grids, are sometimes more greenhouse gas intensive and sometimes less. So if we could think of consuming more electricity when it's cleaner and less electricity when it's dirtier, that would clearly, possibly, not much effort, that would reduce our overall emissions. Point 4 is then, don't throw away all those computers, even if they use a bit more power. Or certainly do some calculations to work out what the medium-term benefit is. It's use the least amount of embodied carbon possible. And here, the difficulty for us is often not so much the stuff we buy ourselves, servers, it's all of the intermediate stuff like networking and consumer devices. Principle 5 is measure what you can. I would extend this to say measure or estimate what you can, because often direct measurement is actually quite difficult, but estimation is possible. If you don't start somewhere with measurement, it's like anything in the SDLC, right? If you don't know how well you're doing, it's very hard to know if you're heading in the right direction. That's really all that point is. For software emissions, it's a relatively complicated process, actually. I'll show you some of that later. But the principle is very sound. If you don't start measuring and estimating, you are not going to know if it's getting better or worse. And finally, this point is beautifully diplomatic. It's point 6 says, understand the exact mechanism of carbon reduction. This could be rewritten as, don't buy your way to greenwashing. What they're getting at is that certain large cloud giants, who are members of the GSF, buy a lot of carbon credits. Carbon credits are simply, you're buying the right to pollute from somebody who doesn't pollute. One of the ways Tesla makes a lot of money. Tesla gets a lot of carbon credits because it produces electric cars that they sell for hundreds of millions to billions of dollars to other companies who want to carry on emitting. The GSF's policy on this is very clear. It's that you should be reducing your emissions, not buying the right to pollute. Because of some of the members of the organization, they couldn't state that quite so directly. So what they said is, understand, and really what they're getting at is, when your cloud provider says your emissions per unit of compute are this, you need to ask them, how did you calculate that? And I'll come on to that later, but as a hint, only one of them calculates it without carbon credits. I'll need you to guess which one.
Quick question here.
Yeah.
So I think these principles are very, very good. But now that we're all moving towards generative AI and almost all the coding we do for developing software Gen AI, and I'm assuming a lot of this Gen AI already have these green software principles.
Not at all.
Not at all?
No. I'd say software that comes out of Gen AI is generally fundamentally insecure. It's fundamentally unperformant, and it has no reference to green software in it whatsoever. Now that may change. Right now, today, after extensive testing, I mean, I left it down 6 months ago, but we've done a lot of testing. I'm sure Zulke are doing a lot of testing now, so you may have a much more up-to-date view than me, but software that comes out of Gen AI needs to check rather carefully for all kinds of qualities.
We have a team dedicated to EIS and green computing is one of the aspects. But that includes things like air conditioning in the offices.
Yes.
And the water as well. Apparently, I've read it somewhere else that every prompt we do costs about 500 milliliters of water. So for example, you write down, hey, you write down, please, and do something like that. It would just cost you 500 milliliters of water that goes into the ChatGPT to cool it down.
Yeah, for the cooling systems. Yeah. That's not emissions, but yes, that's another environmental factor.
Yeah.
Well, we've just diverged from your presentation for a moment.
Absolutely, yes.
Just say, I've counted 13 people in the room, is that right? 3.
A few invisible as well. Online.
13. So put your hand up if you don't want any food at the end of this. There's nobody. Is anybody who's gluten intolerant? Any other intolerances? Yes, I understand. If anybody wants to join Derek in eating other than pizza, we can some chicken, nuggets and things like that.
They're very good.
I don't think I'll be able to stay afterwards.
Sorry?
I don't think I'll be able to stay.
Yeah, we're not gonna stay.
Sorry, there's too much noise in the room.
I won't be able to stay afterwards.
Same day.
Yeah, we're not
Yeah,
staying as well.
we're not staying as well. We're not staying as well.
Okay, so there's actually just 10 of us then.
Yeah.
Okay, thank you.
You could head to a Michelin star restaurant.
I'll get half plant
You
based.
can get that through a BCS budget. You're a better man than me.
Sorry about the interruption.
This is meant to be interactive, by the way. I should have said that at the start, shouldn't I? Before I talked at you for 25 minutes. Yeah, do interrupt me.
It's sparse, so people know that.
Well, I hope so.
Just the way we-
You never know. Might be the first time for someone. There are a few other principles. I'll just go through these really quickly because I realise I am taking quite a lot of time. But most of these came from my PhD thesis, and a few of them come from what's considered good practice in estimation from people like the GSF or the Green Web Foundation. And try and link emissions to business transactions. A lot of people link them to physical, today it's all virtualized, but you know what I mean. Computational measures like CPU usage, disk usage, memory usage, and the business go. Whereas when you say one of your shopping cart transactions creates 4.8 grams of carbon dioxide, that's actually, when they sit up and go, oh, hang on a minute, then we have an ESG unit telling us to reduce that. And they start thinking about it's actually their work producing it. It's not IT doing it as some side effect of their work. Emissions, people, when they start with, often try and take a real micro-based approach to emissions and try and like dive to the lowest level and make something very efficient. They're really a system level concern. And this is where, if you do take a micro view, you miss whole things such as all the client devices. It's very much start at the architectural level. There are micro things to do too, but start at the other end. And you really, really need a cross-functional team. You need business to take an interest, so they actually tell you to spend time and effort on this. You need an application team, because they're probably the ones who are going to have the biggest medium-term impact by changing the way they build and operate software. But you have to have an infrastructure team, so they at least know what you're trying to achieve, and actually they may have all kinds of knowledge about emissions to do with the infrastructure, virtual or physical, which they need to feed into it too. 3 more tactical things is focus on high impact changes. People do like to do things because it sort of makes them feel that they're achieving something. You actually need to check that it's actually going to have a meaningful effect on the emissions of the firm. Secondly, don't ignore the non-technology emissions, but be clear of where they're being counted. In most cases, we exclude all that stuff from our technology emissions because they're being counted in the company's scope 1, scope 2, or scope 3 already. And the last thing we want to do is double count them. This problem is hard enough without double count. And finally, understand the importance of software emissions in your organizational emissions. My example of this would be, we work with a number of deep water logistics firms. They burn heavy fuel oil, hundreds and hundreds of gallons per hour for their fleets. They have a major emissions problem. They also happen to have some data centers. So there's this much coming out of their data centers and this much coming out of the deep water logistics fleet. The software team could help them immensely with data collection, data gathering, modeling and analytics of the deep water logistics emissions. And once that's coming under control, it might be worth looking at the data centers. On the other hand, if you are Google, data centers are your emissions. You've got so many of them, they're everywhere, and quite small changes in how you run them have a huge impact. So just be aware in an organization's context what to look at first. So a few tactics then, things you can actually do with real systems. The most famous tactic, which everyone talks about, is demand shifting. We often actually have quite a lot of flexibility, particularly when we're using public cloud, but not always. If you work for a large financial services firm, you will have data centers in different places. We have flexibility over when and where we can do our processing. We can run, for example, computationally intensive load, or our LLMs, at different times, or we can move workload to different places. We know that electricity grids vary in their greenhouse gas intensity over time. Some of them are, on average, lower than others, but even the ones that are lower vary over time. Therefore, both moving in time and space can make sense. If this is real grid carbon intensity for the United Kingdom, I don't exactly remember when, but sometime in the last 12 months, I think. And this is from midnight to 11 p.m. You can see, I mean, that's 150. The highest is over 300. So it doubles over 24 hours. So it's quite significant when you run it. And of course, this is dinner time and watching soap operas. This has historically always been the peak. When everyone gets home, and particularly in the winter, they start burning lots of energy to heat their homes, switch their lights on, cook their dinners, and watch their devices to see what's happening on soap opera they're watching. And the other one peak, as you would imagine, in the morning. Everyone gets up, makes breakfast, gets their children ready for school, burns power, creating their breakfast, and so on. If you could move some of your business workload from 5 p.m. to 1 a.m., you would halve the emissions from running that particular workload. The other thing you can do is, particularly if you're using a public cloud, you can ask all these dots. This happens to be Amazon, but it doesn't matter, it could be anyone. All of these dots are regions. every region has a different greenhouse gas intensity for operating services within it. And it's a function of a number of things, but energy is a big part of it. Clearly, if you move from a high intensity region to a low intensity region, and you don't have any other side effects, you hold everything else constant, then you will produce less emissions for a particular workload. There are, of course, some trade-offs. One is that can be quite complicated to do. Some people try and do this in real time. There is a debate over whether that's a good idea or not, but let's park that. Some people try and do it in real time. That's quite complicated. And even any of you who've worked in corporate IT will know, moving an application from one data center to another is not a job for the faint-hearted. There's quite a lot of time, effort, and angst in doing that reliably. There's also hidden emissions. I came across this a while ago. A company with the best intentions in the world was moving compute workload to different places because they were doing very intensive compute. It was to do with machine learning on images. What they hadn't really thought about was when they were sort of, they weren't doing it by the minute, but they were sort of chasing lower emissions by moving stuff in not real time, but over a 24-hour cycle. As I say, with the best intentions. What they hadn't really thought about was accessing the data. If the data is in one place and you move the compute a long way away, you're either going to copy all the data or you're going to retrieve it as you need it across the network. And that was creating really quite significant emissions when the transfer and restorage of it was taken into account. So look for hidden emissions. The other thing, Adrian Cockcroft points this out. You might know Adrian, he's a British guy who's lived in California for a long time. He was chief architect at Netflix when they did the big AWS migration, and then he worked for Amazon later. He is a passionate green software advocate and works with the GSF a lot. One of the things he keeps pointing out is if you're a large user, of course, if you're not a huge user, maybe this isn't worth it. If you're a big user, don't do this without talking to your cloud vendor, because they watch utilization in different regions like hawks. And potentially, you could trigger them. He said, literally, Amazon will go and build a data center without telling you. So by trying to do the right thing, you've accidentally caused them to pour a load of concrete in Scandinavia. Now, strategically, that might make sense, or actually might be a terrible idea because your workload's only going to do this for 2 months. So if you're a really big user, actually a scientific laboratory or a big bank or something, a big airline, you want to talk to the cloud vendor as to what you're trying to achieve, and they will have a team that knows how to minimize emissions. All of them have one, whether or not they talk about it very much. The second tactic is quite a lot trickier. It sounds really seductive. It sounds very, very obvious until you think through how you do it on your system. We can often vary the intensity of processing in the system. For example, you can reduce the precision of calculations. You can use sampling instead of full analytics. You can reduce the graphical precision of things. You can even switch off some features at certain times. So once again, we know that the grid varies in greenhouse gas intensity. So if we can keep our system running in the same place, but do a lot when the grid has low intensity, and then throttle the system off and do less when there's higher intensity, then increase again when it gets low, and do this on the 24-hour cycle, this is a very seductive idea. We could reduce our emissions, actually, and almost nobody would notice. The problem is they tend to. Firstly, this can add a lot of complexity to your system. Your product owners might start asking where all of their story points have gone. Said, well, actually, we've built a very clever system for turning off your features when the grid intensity is high. You might go, done what? Why? It needs a lot of buy-in from the business. The other thing is that reducing the service. So, for example, I'm from, some of you may know, from an investment banking background. For us to simply flip risk analytics from full analytics to sampling, that'll be a long conversation with the risk group and the trading desk. I mean, yes, it might be quite possible. It might make perfect sense, and they might be very supportive, or they might go absolutely ballistic because actually they've had very bad experience with the sampling over the years. So, it was interesting. A guy, Charles Humble. He's also very active in this. He posted on LinkedIn a couple of months ago saying, I'm giving talks on green software and I'd like to find people who are doing this. I'm particularly keen to find people who are using demand shaping. And he had quite a few people contact him privately. I Charles and I talk now and again, not a single company using demand shaping contacted him. I'm not sure many people have really made this work. It's a nice idea, and for certain systems, it probably works really well. For a lot of systems, it's really hard to persuade people.
I think most of the time we do use these type of demand shaping, but it's less about the carbon. It's more about moving it to where the prices are low and
That too, of course, often the cloud vendor is encouraging you to go to a low electricity cost region, and that may be because there's low emissions, or may not. I mean, it's sometimes
that does work actually. It does happen.
doing the right thing is cheaper. Yeah,
It does happen actually. It does save a lot of money as well.
good. Third tactic is moving work to the client devices. Do you remember we said client devices tend to exhibit high embodied carbon, low operational, I said carbon myself there, low operational emissions. It's because they're pretty idle for most of the time. If you look at server utilization, a well-run data center servers are 60–70% busy most of the time. Client devices are very rarely anything more than about 10 or 15%, except for little tiny peaks. That means if we could move workload from servers to clients, effectively we get it for zero emissions. They're going to be running anyway. That embodied carbon is a sunk cost. If we can do more processing on the client devices, we're going to produce very, very small amounts more emissions. And we might, because of the kind of large numbers effect, if you've got 10,000 or 1 million clients, you move a relatively small amount of workload off the servers to them. It won't be noticeable on the clients, certainly over their lifetimes won't affect their emissions footprints, but yet you might need a lot less server hardware. And suddenly both emission and operational, embodied and operational emissions go down on the server side.
Have you seen anyone using this model?
Yes, definitely. There are some corporations, but yeah, there are lots of SaaS type companies who are looking at this. And again, it's not always because they care about emissions. It's actually because they worry about their cloud bills, but it is driving them in a positive emissions direction too.
The mobile device, for example, the battery runs so faster.
It can do, yes, and they also might. You've got to be careful that you don't put a load of very heavy memory usage on their mobile device, because suddenly everything will slow down, even if you're not using a lot of CPU. Yeah, I mean, this works where you've got probably quite predictable mobile devices. People have to have a certain scale of them, and there is plenty of spare capacity. It doesn't work so well if you've got
a lot of this crypto mining companies do that, right? A lot of this crypto mining companies.
Yeah, I hadn't thought of crypto mining, but yes, exactly. Crypto mining runs in your browser. Yeah. So you might, for example, pass raw results to the client and process them there. Just get them straight off the server and avoid tying up server compute. Cache more data on the client, use its memory rather than the server's memory. And a case study I'll show you later at an auction company, move resilience mechanisms, because we tend to, I'm a server-side person, resilience is always a server thing. Well, actually, it's perfectly possible to build resilience on the client side too. So smart clients and dumber servers, you can save a lot of server hardware. Obviously, as ever, complexities can be security and data movement problems, and you are dependent on knowing your client devices reasonably well. But then, for example, SaaS companies tend to know the client devices extremely well because they're constantly monitoring. Tactic 4 is measurement. As I said, all emissions measurement is difficult. It all tends to be estimation, but that's okay. We shouldn't beat ourselves up. It can't be precise. If we know about ranges and probabilities, that's a really good start. The cloud vendor dashboards are a good place to start. They do provide some assistance. However, there are a few caveats. Only GCP's cloud dashboard actually uses proper location-based data. Both Azure and AWS are using adjusted data talked about it earlier, using carbon credits. So when you see emissions in a region, for AWS, you don't know what the emissions in the region are. What you know is what the emissions in the region are, less what Amazon have bought the right to emit. So you have to push your solution architects quite hard. Amazon have all the real data. They can supply it, they just choose not to. The solution architects can get it from the sustainability group, who are probably thrilled that people are asking for it, actually. The more pressure we put cloud vendors under, the more they'll take this seriously.
So the data normally we get from Amazon says it's zero because it's all renewable energy and the net zero. So
Yes, because they've bought a lot of carbon credits. Yeah, they're one of the biggest consumers of carbon credits in the ICT industry.
yeah, so they are sharing the data, but the data says it's zero. So
But you need to push back that data and say, could I see the location-based data without any carbon credits? And initially they'll go, no, we haven't got it, but they absolutely have.
I don't think they share that data.
Oh, they will if you push them hard enough and you're a big client. All you have to do is say, we're going to take 10% of our workload and put it on GCP. They will immediately share data. All of the cloud vendors. I mean, Adrian Cockcroft says this repeatedly in public talks. He said it when he worked for Amazon. He said, if you want us to do something, he said, threaten to move workload. He said, that has an almost immediate effect on the entire account management hierarchy.
We've got on-premises data center. Is it usual that you can measure the electricity consumption?
Yes.
They have a separate supply, do they, which is metered separately from the rest of the building?
Oh, absolutely. In fact, most data centers now can do power supply to the power supply to the rows, and recent data centers can do power supply to the rack, and the most recent data centers can do power supply to the board. So they've got a huge amount of power monitoring in the data center. Again, it's not really driven for sustainability primarily, but it's because data centers use a lot of power and it costs a lot of money. So they really want to know where the power is going. But it has a great side effect. If you're trying to achieve sustainability, you can pinpoint what in the data center is chewing lots and lots of power.
You can find the data from the machines as well, so directly. So you could do a top up and a bottom down.
Yes, so the other thing is you can do, of course, is estimation. If you go to manufacturer spec sites, they're all now publishing quite detailed lab results of energy usage. So you can go, well, we tend to average this kind of usage. In their lab test, they got this. That's good enough to start with if the data center people don't have the data. Because not all data centers collect the data which their racks are, which their power supplies are producing. A few of the really big vendors in this area, apart from the cloud vendors themselves, are electricity maps, which I mentioned, watt time and climatic. They're all providing sustainability data. You can use them free of charge at a small scale, and at a large scale, obviously, they charge for API access. And then there's lots of sort of almost common sense tactics. Patterns.greensoftware.foundation has lots and lots and lots. For example, only actually commission what you need in the cloud, switch off what you're not using. Consider compression for large data sets, both at rest and also in motion. But of course, what's the trade-off? Burning lots of compute, using a lot more energy. You might be forcing people to upgrade their CPUs or add more servers. So actually, a lot of these are, it depends. Caching static data is just the same. How much more memory will you use? How does it affect the overall compute shape? Minimizing stored data. Lots of companies do sort of keep data a very long time, but they don't necessarily need to. Often, actually, they'll only ever use a fraction of it or a processed form of it. And they could just keep the processed form of it, but no one likes to throw data away, do they? So that means that the data sets grow infinitely. And of course, the classic one, which Amazon will tell you to do, turn off test and development environments when you're not using them. So that's kind of conventional wisdom for mainstream software systems. And then that was how it was 3 years ago. And then along came AI, and every green software person put their head in their hands. AI-based systems require massive amounts of compute, memory, and storage, and you can't get away from it. That's just the way it is. They didn't used to, but they now do, and that's the way the field is. So it's no surprise they're an utter sustainability disaster. They're specifically why Microsoft thinking, I think it was 2023, that their emissions went up by a third, which for a company the size of Microsoft, that's pretty serious level of emissions. And I mean, Google and AWS, Salesforce, they will all have this because they're all training models and they're all running loads of inference. Well, there are a number of key determinants of what the environmental impact are how big is the model, how many parameters are, how many weights and biases are there, how long did you have to train it? So how many times did you have to calculate those numbers over and over and over again, checking the results to try and get to all the minima? And then once you've got the model, how often do you query it? And of course, for someone like OpenAI, they'd rather not tell you because the results are pretty awful. They're massive, massive amounts of compute for training. And of course, we're all asking it for our recipes. What can I do with bacon and sausages or whatever? And all of that is just constant inference that they're running across massive compute clouds. So they are using an awful lot of compute. The way to think about it is to think about it in a sort of life cycle sense. There is a certain amount we can do as consumers. We can just be a little bit mindful about what AI models we are querying and how often we query them, and are we querying them for something meaningful. That is not a bad start. That's a very micro level optimization. We really need to think about is the whole life cycle of the model. This is a data science model called CRISP-MLQ. It came from Germany. You might not be totally surprised. It stands for something like something industry standard, something for machine learning with quality. I can't remember exactly what it stands for, but in German it probably makes sense because there's probably long words that fit together and it's all very logical. It works less well in English, but it is what it is. Anyway, it's a bit like an SDLC, but it's for how you build and operate model-based AI systems. And that's an existing thing. What we can do is overlay, and it doesn't have anything in it at the moment about sustainability at all. They just haven't added it to the model yet. So they can thank me later, I've done it for them. Step one is what we might call systems analysis in old money. It's understanding the business and understanding the data to understand what problem we can solve with AI. This is the point we need to start thinking about emissions. And as a software architect, I say, we need to think about emissions as a quality attribute. In other words, an attribute of the system, just like performance, just like scalability, just like security. Because we know what happens if we leave security to the last minute, we get an insecure system. We know what happens if we leave scalability to the last minute, we get a system that won't scale. What's going to happen if we leave emissions to the last minute? We get a system with loads of emissions. It's just that simple. We have to start thinking about it early. Then during the data preparation phase, this is collecting data sets, cleaning data, characterizing data sets so you know how you're going to use them in model training. Use existing data sets if at all possible, because collecting data tends to involve lots of emissions. And minimize the amount of data, minimize how long you keep it, and minimize the amount of processing you think you have to do to it. When you're actually doing the modeling phase, creating models, well, the first one, the most fundamental one, all AI people now say to you is, you could use someone else's model rather than starting from scratch. But of course, AI people like to train their own models if they possibly can, because it's kind of fun. But it's one of the most emission-intensive parts of the whole process. Can you minimize the model size? Bigger is not always better, and particularly from an emissions perspective, it's always worse. Once you've got a model, could you shrink it? Will it still work well? For example, if you quantize it, use smaller numbers. And if you must train, could you demand shift that into a time or a place that will minimize the environmental impact? The other thing is, could you use specialized hardware? Some chip manufacturers are much more environmentally aware than others. I'm not going to name names, but let's just say that one of the biggest names in AI has got almost nothing to say on energy usage or environmental sustainability of their chips. Others are much more interested in it. So having hardware that's well suited to the task, and ideally is very it's very energy efficient. When you're evaluating models, that's when you can consider shrinking them. If you've created a big one, okay, all that sunk cost, you've trained it, but actually could you shrink the model? As you shrink it, is the performance good enough? Because inference is where you're going to burn lots and lots of power. When you're using it, can you deploy it in a low greenhouse gas intensification? Again, can you demand shift usage? Can you demand shape the usage of the model so that we minimize the impact? And then when we're monitoring and maintaining it in the CRISPR model, this is all about, is the model still performing well? And of course, that's very important. But are we also thinking about what is the greenhouse gas emission footprint of this model? How much are we using it? Are we using it a lot more than we thought? Or are we having to use it, for example, in a region with high greenhouse gas intensity, in which case should we go back and think about quantizing the model now? Because we realize we're producing a lot more emissions than we expected. So a couple of quite quick case studies. I'm mainly going to do the first one actually. This is an example of tactic 3, I think it is, moving to the client. This is a real one, it's from my PhD thesis. An online auction site realized they were having a big environmental impact. They did lots and lots of analysis. They were real pioneers in this actually. This was back 2015 they started. We worked with them in 2016, 2017, so quite a long time ago. After quite a lot of analysis, they realized that actually embodied greenhouse gas was their biggest problem, or so they thought. What they noticed was that their usage of the machines was quite low, the utilization level. The reason for this is they had extremely resilient back-end services, and they used a lot of hardware to achieve that resilience. So they replicated services massively across many, many machines, normally across sites, so that whatever failed, they could fail straight across to something else. And all this was done on the server side. So it was layers of machines sort of checking each other and moving workload around. They realized that if they could simplify this, they'd save a lot of emissions. The fact that they realized it would save them a massive amount of money didn't do them any harm either in terms of getting buy-in. The CIO went, yeah, emissions, yeah, whatever, about the dollars. Yeah, that'll be cheaper. Good, go and do that. And the key insight their software architecture group had was clients fail a lot. When they looked at their unfinished transactions, of course, there are some where they've had a server failure, and there's a huge cluster of failed transactions around one server. But actually, when they look at what fails, clients fail all the time because broadband goes down, and people switch off their mobile devices, and browsers crash, and JavaScript errors. There's all kinds of stuff goes wrong with the clients. So actually, when they looked at it, massive heap of client-side problems, relatively speaking, a small heap of server-side problems. Just the server-side ones look dramatic to the ops people because they can't see the client-side ones. They just time out. So actually, if they could move redundancy handling to the clients, it actually wouldn't make much difference. It would be, from a systems architecture perspective, the clients are going to fail anyway. So let's put the resilience on the client side. And if the client fails, it doesn't need to worry about the resilience. If the client continues, good, the resilience mechanism is there. So before the hand, they had an auction app running on a phone. They had request handling. These are massive farms. These aren't single machines. Massive farms, request handlers, and all their business services were massive farms of redundancy with multiple layers of redundant handler in it. It was all. I mean, it was really good engineering. It was really, really solid. A lot of them, I think, had come from IBM at some point. I don't mean that in a derogatory way. I mean that they really knew about resilience. So it was a very reliable site.
The other reason for moving the redundancy to a client is it because when one client is down, it's impacting only one client versus one service.
Two reasons, yes. One, the clients fail a lot anyway. And yes, if the client gets it wrong, it's one client affected. The other thing is, what they did was, they spotted that they had 10% of their services, roughly, were transactional services. So that's where actually it goes wrong in the middle. It's like a payment. It really is quite painful to try and undo it. You want to minimize the errors in those. But the vast majority of their services were critical transactions. So what they called those standard services. So what they did was they built a proxy in their app that was smart enough, it had all the logic in it to know that if something times out or if something returns an error, here's what to do. Basically, of course, they had they had lots of DNS records to give the client hints as to where to look next, and clients could daisy chain down until they found something, and eventually the client had all the logic for, I'll have to give up now, tell the user that, try later, or tell the user will keep their transaction safe, or whatever it is. All that moved to the client side. They just maintained all that resilient stuff for the transaction services, 10% of the data centers. 90% of their data centers, they stripped out a huge amount of hardware. I don't suppose they threw it away, but they could reuse a huge amount of hardware in much simpler services. And they surprised themselves. They reduced their server estate for the non-transaction services by 50%. So that's half of 90%. So 45% of their estate, they could either recycle, reuse, or decommission. This meant they had a huge quantity of embodied emissions would be avoided going forwards. They also, this is of course how they justify doing it, the energy usage dropped by 50%. So that was huge for their energy bill. And of course, they'd be buying less service in the future too. The second case study is demand shifting workload. This is for AI learning. I'll go through this quite quickly, so we've been talking quite a while. But machine learning workloads are obviously very resource intensive. This team was classifying Japanese characters. in photographs or faxes maybe. The team that did it was worked for in Davos, Serbia, and most of them are from Belgrade, apart from Usman and James, who are based in London. And I put them up, one, because they're really, really great, and they worked really, really hard, they did a great job. But two, this wasn't two people for a morning. That entire team was involved in this project, and it took something like 6 to 8 weeks. They weren't all on it full time. I hasten to add, I mean, Usman kind of popped in at the start and at the end. James was sort of involved a couple of mornings a week, but some of them were full time on it, and a lot of them were part time. So it requires a lot of skills, and that's what was a surprise to us, frankly. On a specific day, they estimated that at 8 o'clock in Western Europe, running one of their training runs would emit 125 grams of what's known as carbon dioxide equivalent, in other words, greenhouse gas. If they could shift region, they could immediately save about 25% of that. And if they could shift the time as well, they could save about another 15%. So that'd be a 40% saving. And that's well worth chasing. This was done in a client context. The client was going to put this in production anyway. But at some point, I think our green software pod had gone to them and gone, "Had you thought about your emissions?" And they went, "Not really." And they went, "Well, we could think about it for you." So they gave them this project. What they did was they had a machine learning pipeline. This is the thing that trains and checks the model. And it runs in different cloud regions, and it's all containerized workload, as you would imagine. We used a Green Metrics tool, which is an open source product, which allows you to try and estimate a number of metrics, actually, but particularly power usage and emissions. It collects data from your workload. On the machine, it collects your runtime statistics, and so it runs inside a little runner. And so the machine learning pipeline is kicking off these workloads in different regions. And we've got a scheduler to kick off the workloads at different times, or if somebody really needs it, they can demand one as well. So we needed some information about the emissions, the greenhouse gas intensity of the electricity that was being used at the time. So when the machine learning pipeline ran, they built this Azure functions-based utility that it retrieved metrics. So the Green Software Foundation has an open source carbon aware SDK that allows you to get data related to how green your software is. And one of the things it can do is it can query electricity maps in a really straightforward way. So they used electricity maps and they wrote a relatively straightforward bit of Python actually to call the SDK, get the current information from electricity maps and store it in a database. So they knew at a point in time when they were running what the greenhouse gas intensity was. And then, once they got all that running, they installed an instance of Green Metrics tool and Postgres database to keep these consumption metrics in. Then the Green Metrics tool would allow them to, at any point in time, say, for all of our jobs, when those jobs ran, what was their greenhouse gas footprint? Obviously, what Green Metrics tool is doing is it's using the electricity metrics that were retrieved by the retriever as a side effect of the pipeline, along with the consumption metrics, which its runner had collected, put the two together, and then uses a whole lot of heuristics. These are estimates, not precise measurements, a lot of heuristics to work out what's the likely emissions for a particular one. Just to, you were not expected to read through this. This is an Azure DevOps pipeline. It's just to highlight the fact that it's not as straightforward as we thought it was going to be when we started out. It was quite complicated. That's the workflow. I mean, two interesting bits are, firstly, you've got to find the right region to run the thing in. And there's a lot of heuristics actually embedded in the logic about, because you don't want to be ping-ponging between regions because it takes time and creates emissions. So it's like lots of problems in computer science. Just because you've crossed a boundary, you don't want to immediately take an action. And then, do we need to start immediately? And do we need to change the region or keep the region? So there's all the logic to work this out and then actually do it, to call external infrastructure as code, code to it build something if it's missing, or to move workload if not.
For a completely different reason, could I ask whether they developed this as a function app or a logic app?
I don't know. I think they did it as a function app.
Yeah, that makes sense. So anything complicated,
Yes.
It's absolutely a nightmare.
Yes, because yes, changing anything becomes a real time. But I think it was a function app. Yeah. And then what this gave them, this is the green metrics tool. This isn't anything the team built. This is just sort of, well, actually, you'll undertake it, but because it's open source, it's straight out of the box, really. This gives them energy metrics, tells them for different kinds of runtime resource what was used, and then somewhere gives CO2 estimates for compute and memory and storage. And so it allowed them to start thinking about when should we run this, where should we run this? And the client was actually really intrigued. They just never thought about that because they did a lot of these trading ones. This wasn't like, 2 a day. This was hundreds a day. They never really thought about the fact that without a hugely complicated piece of software, we could halve our greenhouse gas emissions from one of our most greenhouse gas intensive pieces of work.
Have you got some idea of the return on investment for that 2 weeks involvement of the team?
I can confess this was our investment, so there wasn't a direct return on it. The client got it for free, so no, I mean, I'm not really sure.
But I think what was the savings you could find out from this?
They would have saved something like 40% of their electricity, but it's cloud compute, so it wasn't their electricity directly. I don't really have those numbers. In fact, I think I don't have them because I couldn't talk about them. Their cloud bill would have been lower, but I'm not sure exactly what. Okay, so hopefully I've inspired you that green software might be something you might want to take back to work. What would you actually do? First hint is don't start trying to optimize loads of code and rewrite your Python into Rust. Sounds great fun, but it's not the place to start. The first place is to become informed about it. I mean, generally that's why I'm giving this talk, because I just want people to just go and learn more about this. There are a couple of books, not a lot, but there's a couple of books. There's a couple of very good websites, and there's some training. There's some organizations you can join if you're enthusiastic, all of which you just get the basic knowledge about how all this works. The first thing is, and if Anne Curry, who's a notable author of this field, was here, she'd immediately say, just do less of everything, which is harder than it sounds. It's like designing the simplest thing possible, isn't it? It's a lot harder than it sounds. But she's right. If we do less, we're broadly more efficient. We think about consumption, but we use less hardware and less energy, we will reduce our emissions. It is that simple. She's absolutely spot on. The thing that a lot of us can do quite quickly, though, is start thinking about using clean energy. Cloud providers, especially if we push them for real numbers, will give us some idea of the emissions in their different regions. If we're running our own data centers, our data center staff can definitely tell us at a gross level, with a bit of arm twisting, at a fine grain level, where the power is going. And then we can get all the data we need. It's all publicly available, mostly on time, mostly in real time in most economies, as to what the emissions implied by that power we're consuming is. It's at that point, the kind of architectural tactics and patterns I've been talking about start to be relevant. Once you've done all the basics, which actually, you get to here, and a lot of people have had really quite a big impact on their emissions at that point. That's the point to say, now we can start doing the fun stuff, like moving workload around the world, or changing the way that we process things, or making things more efficient. And there are, quite a few patterns you can follow. The one word of warning I'd have is that the GSF, Green Software Foundation, have a very voluminous pattern catalogue. If I have one criticism of it, I think it's a great piece of work. The one criticism is the trade-offs, particularly the emissions trade-offs, are not very clear in the pattern descriptions. So they will say things like move workload to an alternative region without saying, but not if you have to move a lot of data, or calculate the side effects of moving your data. So you do need to think about that yourself. They also have got some which aren't related to emissions, such as they have a recommendation to stop SSL at your organizational boundary, which as a security engineer makes my hair go white. That's such bad advice for nearly all situations.
So one of the things we have seen is a lot of the cloud providers say that just moving to the cloud will make you save 70%.
Yes, they love that kind of blanket statistic. Yes, yeah. Stick with us, it'll all be fine. Just spend more. They might be right, but I mean, unfortunately, you really have to estimate it yourself.
Would that be part of the architectural pattern?
Well, actually, that's possibly from here, actually. is that you work out what is your environmental footprint in your data centers. If we were to move into the cloud, what is the environmental footprint? Now you want to do that in a sampling sense. To do that comprehensively for an estate, that would take years. But you can do it for key applications.
So you're saying do less means you have lesser now scope 1, scope 2, and more of scope 3.
And you may have, that's the thing you've got to assess, is that am I simply moving the emissions or am I actually reducing the emissions? And then finally, you can do optimizations, which is where a lot of people start. There is an infamous academic paper floating around. It's like 15, 20 years old, I think, where they compare the runtime efficiency of different languages. And you will not be surprised to hear that Python doesn't come out very well against highly optimized C. Go figure. They're used for totally different jobs, and that's been waved around by lots of people in the green software movement as you should rewrite all your software in Rust and C. Clearly, the return on investment of that, never mind financially, just in terms of emissions, can often be actually very low indeed. It really depends what you're working with is. And certainly all of these things are almost certainly higher return on investment than starting with a code optimization project. But of course, code optimization project is quite fun. So quite a lot of people like to start there. And if you want to, knock yourself out. But just pointing out, in terms of having impact, as we said at the start, actually starting further down the pyramid works better.
So how much percentage do you think is code optimization in this?
Depends on your workload. So if you're doing lots and lots of risk calculations, they're probably not in Python today, let's be honest. But so if they were in Python and you were to rewrite it into optimized C++, you're probably saving something like 90% of the compute and 50% of the memory. So yeah, it could be really significant. But it depends whether that processing is significant in your overall emissions. And if you're the National Physical Laboratory, or I'm talking at a conference in Germany later in the summer, where it's the matter research scientists, Large Hadron Collider type people, for all of Germany, and they're all sending their software experts, who are all physicists, you can imagine. And they've already thought about this quite a bit, but they want to talk to people who are outside their community. Well, you have to admit, the amount of compute they do, making it 20% more efficient probably has a big impact. But for many, many systems, we know that they're bound on waiting for the database, they're bound on relatively straightforward in-memory data manipulations. Optimizing the compute's not going to make that much difference.
There's also something you can do, which is to use specialized numerical libraries, which
absolutely, yes.
So your actual interpreted code is only executing. Yeah.
That's a very good point. Yes.
There's a company called Mosaic who approached me to talk here. It was a bit commercial, so I won't do that one. But they're a Danish company, and they've developed these algorithms to optimize them to the nth degree.
Right.
So if you've got an optimization problem or pattern recognition.
Yeah, exactly. Effectively, outsource your optimization if you can to someone who's done it already. Yeah.
Yeah, and I'll say up front that this is an area which sits right in my PhD, but there's a thing I think which is missing from that, which is at the make or buy stage, because you haven't really talked about the production of software, and there's a big difference, because if you assume all software systems are already written and are all already as efficient in some sense as they need to be, then all the strategies you've talked about are great, but there's a massive impact when you're producing the software in the first place. And in practical terms, I mean, ignoring AI for the minute, which is a bit of an unknown, but most software is not developed from scratch, if you like. It's developed by wiring together existing components. And yet there is, so first approximation, zero information about the efficiency or energy usage of any of these components. And so I think there's a huge amount to be gained from including that kind of factor, and including it when you're looking at evaluating a component or a server or a library or anything like that.
Yeah.
And this is my personal push, is I want everybody to push for more information for that, and to push for that to be included in the software design and architecture process. I mean, some of my own stats, as part of my PhD, I built an energy measurement test rig and compared different software on it. And you know, it's nuts because if you take WordPress, okay, extremely popular, 60% of the web is WordPress, according to some of the stats, okay, that took something like between 20 and 25 times as much energy to serve the same website as an equivalent static site. Now, sure, you might need the dynamic behavior, but most of those 60% of WordPress sites around the world don't. And so just that simple software choice is having a huge impact, because if you think about not just how many sites there are, but how many times they're being queried and how much, you know, how much of everything is all multiplied and multiplied and multiplied. And for me, that's a key thing which should be in here, is about choosing the right things so that you build an efficient system in the first place. Anyway, sorry, that's a minor.
Yeah, that's a great point. We should lobby for that to be in the software bill of materials.
Yeah, I really think we should.
People publish them. I'm not even, I'm aware of that factor. I've not thought about it deeply at all. So let's talk about it afterwards.
I suggest you move ahead because
I'm just about finished, actually.
Food is on its way, and
Very briefly,
5 minutes.
There aren't huge numbers of resources to learn more. There are a couple of books. The book, the one the GSF talk a lot about, is Anne Curry, Sarah Sue, and Sarah Bogman's book. It stops a bit before all the practical detail, but it's very good at understanding the factors you should be thinking about. And Anne is a brilliant writer. She writes science fiction at a very high level as a hobby. So it's a very engaging read. A slightly quirky book is by Ioannis Kalakis, I think is how you pronounce his name. The reason I really like it is not so much it's definitive or he's a brilliant writer. He's very tangible in stuff you should actually do and how to do it. And I think once you've read the first book, the second one's quite an interesting addition. And then the third thing is that there is a free course, thanks to the GSF and their funders. The Linux Foundation has a free course on building green software with a little certification at the end. And I'd like to get all developers doing that just for awareness. And then the organizations, Green Software Foundation, have talked a lot, very corporate, very big company driven. Exactly the opposite if you don't like big companies, climateaction.tech, totally grassroots based, groups of enthusiasts around the world who are interested in making technology in general more sustainable. Others are the SDI, this digital, something Digital Infrastructure Alliance. I can't remember what the S stands for. They're quite European centric and they're very hardware centric at the moment. They're trying to move more into application software, so something to get involved with. And then a very practical group by the Green Web Foundation. They run online training on a regular basis. It's quite cheap, where they'll explain the basics and they run a much more in-depth course. And they're the people behind co2.js, if you've come across it. That's their software library, which is open source, which you can use with web applications. And then electricity maps, watt time and climatic. That's where you can get data. And the two specifications, which are not in themselves fascinating, but they're really good at causing you to think about factors to do with emissions you might not have thought about, are the SCI spec, which is now a NISO standard from the GSF, loads of money behind it, loads of publicity. A really interesting standard called the Tech Carbon Standard, which is a slightly different view of it, from a very small British company called Scott Logic, a very small digital systems integrator, I think based in Newcastle. And yeah, I mean, they've done that all by themselves. They're trying to gain awareness of it. It's well worth a look. You mightn't completely follow it, or you might still use the SCI, but it just gives you some more things to think about. Thanks very much.